Okay, so the next thing to discuss is the idea of the sort of expectation of a random variable and the variance of a random variable. Okay, so as we discussed before, like right at the beginning of the course, we said, if you throw a dice 100 times and ask what number you expect to be heads, well, you expect 50 to be heads, because, well, it seems it's equally likely to have tails to heads, so it should balance out 50-50. Okay, but how do we go about sort of making that into a mathematical definition based on our notions of random variables and probability distributions, etc.? Okay, so, well, the definition of the expectation of a random variable as follows. The expectation, or mean as it's sometimes called, really we can say mean a bit more when we've got data associated with it, of a discrete random variable x is, well, it's denoted by e to the x, a bit like my p from before. Okay, I've written it like this. Okay. Okay. We often use square brackets around expectations. I don't know why necessarily, but that just seems to be what people do. And this is really the sum of all the outcomes that can happen to the random variable, okay, times the probability of each outcome. Okay. An interpretation of what this is might be, we could kind of think that we've got sort of 1 kilogram corresponding to the weight of all of these probabilities, okay, and then we're sort of placing that weight along a line at different positions given by x. So let's suppose, for example, x was a random variable that happened to be equal to -8 with probability, WP here means with probability, just to say that this means with probability. Okay, so with probability, say, 1/2. Okay, and then I have it equal to 2 with probability 1/4, and equal to 4, okay, with probability let's say 4, 1/4 as well. Okay, so actually I'm going to change these. Right, this is fine. Notice that the expectation of this random variable, okay, is going to be, well, -8 times 1/2, so we're going to get -4, okay, plus 2 times 1/4, which is going to give me 1/2, plus 4 times 1/4. Okay, I'm going to add 1 to this -4 plus another 1/2, which is going to give me sort of -2.5. Okay, so what this is sort of doing is I'm sort of taking this line, alright, and on it I've sort of got 0, I've got 2, I've got 4, I've got -8 over here. And you can imagine putting sort of a weight in each place. I put a weight that's 1/2 kilogram here, and I've got a weight that's 1/4 kilogram here, I've got a weight that's 1/4 kilogram here, and I sort of think, where on this ruler do I need to put my finger, okay, in order to balance this? Okay, and it turns out in this case that if I was to essentially put a force here to balance, okay, and this will be the right place to completely balance out the weights. Okay, so that's sort of the notion of how this is sort of the mean or the middle of this distribution. Okay, from this there are sort of various properties associated with the mean. Okay, so let's just go through these. So some properties of the expectation. Okay, and I'll maybe collect these together in a lemma. Okay, so let's have these in a lemma. So number one, that we can take functions, for example, of our random variable x. So for a function g, okay, I can look at the expected value of g of x, right? We find that well, this is really just creating a new random variable. Okay, so we take something from our sample space, apply it to x, and then apply it to g, and that just gives us a new random variable. We want to calculate the mean of that. Well, it's sort of as you'd expect, that we essentially look at g of x and multiply it by the probability of each x occurring. Okay. Okay, so one specific function that's quite of use is to note that for positive constants, or not even positive, just constants, sorry, for constants a and b, okay, let's say they're both real numbers, then e, the expected value of a times x plus b, is just equal to a times the expected value of x plus b. So this means this is a nice linear operation, okay? So it can take things out in a nice linear way, all right? For two random variables, which we do know how to put on the same probability space, then e of x plus y is equal to e of x plus e of y. Okay, and so why did these sorts of things hold? Well, really this expectation is just a sum. It's just sort of a weighted sum. Okay, so you can notice here really we're just summing up, okay, the value of x with some weights attached to each outcome x, alright, outcome of our random variable. So all the sorts of things that we expect to happen with sums are going to sort of happen with expectations, okay. One thing to say is, in general, it's not true, it is not true that if we multiply together two random variables, in general, okay, but if x and y are independent, then it is true that e of x times y is actually equal to e of x times e of y. Okay, so maybe let's try prove these. I'm not sure if I proved them in the notes, so I'll just have a crack at them. So first one, well, e of g of x is really equal to, well, we've got this random variable that's g of x, alright? So it's really sum over the values of g, okay, times the probability that g of x is equal to some number g, okay? But then this probability is really a sum over all the values of g times g plus the sum of all the values of x such that g of x is equal to g, okay? And then we're applying the probability that x is equal to x for each of them, okay? Why is that? Because, well, this probability is really just exactly this thing here, alright? Then what I could do is just sort of rearrange this sum a little bit, and notice this is really just summing over all the values, summing over all the values of g and then all the values of x that give that value of g, which is the same as just summing over all the values of x. Okay, so I could just rearrange this sum, and notice this is the same as just summing over all the values of x times g of x times the probability that x equals x. Okay? Alright, next one. Number 2. Well, number 2 is really just sort of a consequence of the first one, but let's do it quickly. Okay, this is just the sum over the values of x, okay, times a of x plus b times, this is a multiplied here, times probably x equals x. That's just the definition. This is just the result from the first part applied to this specific function. Alright, and then this is just a sum. I can multiply the probabilities through and separate out the sums. Okay. Okay, like this, plus sum over x, b, probability that x equals x. Okay, and then this sum is going to just sum to b, because the sum of all the probabilities is equal to 1, and this is going to give me the expectation of x. Okay. Alright. Okay, next one. So, well, maybe I won't do the next one because it's just really the same as the first one. Let's do it quickly. This is kind of the same as the last one. It's the sum of all the values of y and x, of x plus y, probability that x equals x and that y equals y. Okay? Because I haven't really defined what I meant by this, but notice it's just some function of some random variable with a random variable z, which is this random variable added to this random variable. Okay? So just look at the probability that that random, the probability of the values given times the values of the outcome. Okay? So, okay. So now I can separate this out into two parts. Okay, I can look at the sum over x and y, the probability that x equals x and y equals y, okay, plus the sum over y times y, the probability that x equals x and y equals y, okay. And notice, I sum over x here, notice if I sum out the values of y over here, okay, what I'm doing is I'm summing out all the possible things that can happen. So notice this stays fixed as I change y, and if I sum out all of these, I'm effectively taking the union of all these AND statements. Okay, so we could think of the event that x equals x being the union over all y of x equals x and y equals y. Okay. So in other words, and these are all disjoint events, okay? So we've got that the probability of x equals x is equal to the sum over y of the probability that x equals x and y equals y, right? So in other words, so sort of using this fact here, right? I can see that this is really just equal to the probability, the sum over x of the probability that x equals x, and this over here is really the sum over y times y of the probability that y equals y by the same argument. So we've got e of x plus the expected value of y. Okay? Right. So the next, it's not true that e of x times y is equal to e of x times e of y. Okay? So let's see that. Let's suppose, so it is not true that e of x times y is equal to e of x times e of y. For example, we could let x, let's suppose we throw a coin and that x is equal to 1 if the coin lands heads, and equals 0 otherwise. Okay? And let's suppose that y, I don't know, let's say it does the opposite, is equal to 0 if the coin throw, if the same coin, let's just say, if the same coin is heads and is equal to 1 otherwise. Okay? Now if I multiply these together, in either outcome, note that x times y is equal to 0, always, regardless of the outcome. Okay? But e of x is equal to a half, and e of y is equal to a half. But, well, if x times y is equal to 0 always, then e of x times y must be equal to 0, which is clearly not equal to e of x times e of y, which is equal to a quarter. Okay? So you can see that when there's dependencies between the random variables here, x and y, okay, both are very heavily dependent on the outcome of a single coin throw, okay, then we cannot expect the expected values of the multiples to be the same as the multiples of the expected values. Okay? Okay, so why is it true when x and y are independent? So if x and y are independent, okay, well, let's have a look. Well, e of x times e of y is really just equal to the sum over x times the probability of x equals x multiplied by the sum over y, probability that y equals y. Okay. And then this is equal to the sum, well, I could expand this, so for each x here, okay, I multiply by its corresponding value of y, and then do that for every x. Okay. Okay. Now let me just put this y and this x together here, just to rearrange slightly. So just move that over to here, that value of y. Right. And then notice I've got x times y times the probability of x times the probability of y. Okay? But then, well, this here is just equal to the probability that x equals x and y equals y. Okay? So what I have is this is just the sum over x and y, x times y, times the probability that that occurs. We get exactly x and y. Right? And then this, by definition, is equal to the expected value of x times y. Alright? Right, so that gives a few properties associated with the expectation. Alright? So just to give sort of one further short example, using one of these facts, is that we let, as described at the beginning, we let y be the number of heads from 100 coin tosses. Okay, then we have from that the expected value of y should be 50. Okay, so we're just reconfirming our intuition here from before. So let's answer that. Well, we can say that y really is the sum, okay, of 100 random variables xi, where each xi is the outcome of one of these coin tosses, the ith coin toss. Okay, so this is equal to 1 if the ith coin toss is heads, and is 0 otherwise. Okay, notice I can work out the expected value of each xi. Alright, well, with it's going to equal 1 with the probability that xi equals 1 plus 0, the probability that xi equals 0. Alright, now then what we can say is that, well, we know that each of this is equal to half and this is equal to half. Okay, so the expected value of xi equals a half. Alright, so then the expected value of y, okay, we can say is equal to the expected value of these 100 coin tosses. Okay, and one thing we know we can do is if we sum up random variables, okay, it's the same as if we summed up the expectations. Okay, so notice, although we stated this just for 2 random variables here, we could have quite easily done it for 3 or 4 and we still would have got the same result. Okay, because notice, just to explain, that we could say e of x plus y1 and y2. Okay, we could think of y1 and y2 just taking the same role of this y here, and then by this calculation I have that this is equal to the expected value of x plus y1 plus y2 by this result, and then I could apply this result a further time to see that this must be equal to the expected value of y1 plus y2 plus the expected value of x. Okay, so I can split this up as many times as I like, basically. Alright, in other words, what that's really saying is that I can, instead of taking the expectation of the sum of 100 items, I could sum the expectation of 100 items. Okay, so really this is the same thing as summing 100 expectations, and each of these we know is equal to a half. Okay, so it's going to be 100 times a half, which is equal to 50. Okay, now it seems a kind of easyish calculation from the way I've given this, but one thing to say is it's easier than, say, working out something like the probability that y equals 52 and then timesing that by 52, okay, and doing that for every number that you can get. Alright, so it's easier than, say, working out the calculation this way. It involves knowing what all these probabilities are. For example, the probability that you get 52 heads, or the probability you get just one head out of 100 coin tosses, doing that for each one, then summing and calculating. You can get it to work that way, but this way is considerably simpler, and that's because we've employed a couple of these rules about summing expectations. Okay? Right.